momentum and impulse momentum theorem. So just a review, brief review. Momentum is denoted by P. Okay, it is mass times velocity. Momentum is a vector quantity. Vector quantity means it has both magnitude and direction. So that's why you need to use arrow to represent momentum. This arrow means it's a vector quantity. And to change momentum of an object from, let's say, some initial momentum to some final momentum, you need to apply force and for some time. Okay, meaning you need to apply impulse. Impulse is the quantity that depends on both force and time. So impulse changes the momentum. And in symbolic form, impulse is force times time. Change in momentum is final momentum minus initial momentum. You can also write this as Ft is equal to final momentum is initial momentum, final momentum is mv final minus mv initial. Okay. And sometimes when you apply different forces, like you're applying different amount of force on an object. So initially you're applying increasing force. Okay. You apply maximum force at some time, and then you apply less and less force. Okay. Just like when you hit a ball with a bat, when the bat touches the ball, you start increasing. You start applying more and more force. Okay. You apply maximum force at some point, and then when you retract the bat, then the force decreases. Okay. So when you apply the force for some time, you change the momentum of this ball. Okay. And that momentum change is given by area under this curve. Okay. So find the area under this curve. That area gives you impulse, which is also change in momentum. We talked about that last time. Just a review. So let's look at number 3 on worksheet 14. So how much impulse is needed to catch a football that is traveling at 27 meters per second? So football is traveling at 27 meters per second, and when you catch it, it comes to rest. Okay, so final velocity would be 0. So this one has initial momentum of mvi, and this one has final momentum of mvf. So there is change in momentum, and that change in momentum is given by impulse, and that's what we want to find. So for A, impulse is final momentum minus initial momentum. Final momentum would be 0 because after you catch the ball, it stops to move, 0. So that's negative mass times velocity. Mass is 0.4 kilogram. Velocity is 0 minus 27 meters per second. No, sorry, we already used the 0 for the final velocity. So initial velocity is 27. So do the math, that gives you the impulse, which is 10.8 kilogram meters per second. Okay. Impulse is also expressed in the unit of Newton second, because question.
Sorry, that would be negative.
Oh yeah, sorry, negative. I forgot negative sign. Yeah. So impulse is force times time. Okay. Force is measured in newtons, and time is measured in seconds. So instead of kilogram meters per second, sometimes you can also use Newton second. Okay. Both are same, equivalent. Now let's look at B.
Would that graph look upside down? Like if you were to graph that, would that be in the fourth quadrant?
Yeah, so there will be upside down. Yeah. Force. Yeah, so it will be negative. Yeah. Okay, so let's look at the second part. If the player stops the ball in 0.02 seconds during the catch, how much force will the player exert on the ball? So we know impulse is force times time. Okay, and if the force is changing, you can call it average force, because force is not constant, it's changing. So impulse is average force times time. But if it is constant, you can just write impulse is force times time. So this is negative 10.8 Newton per second. Okay, so we want to find force. So force would be divide both sides by time. You get negative 10.8 Newton per second, Newton second, not per second, over time. Negative 10.8 Newton second over time is 0.020 second, and that gives 540 Newton. Okay, that's the force the player exerts on the ball. And then C is the ball will also exert force on the hand of the player because of the Newton's third law. For every action there is equal and opposite reaction. If this is action, then the force of the ball on the hand is reaction. So force on the player's hand is negative of that, which is 540 Newton. Okay, equal but opposite. That means positive. Okay, so that's okay. So we have more parts here. We have D. So why don't you guys try D? It's same kind of question. So it's asking what would be the average force if the time is 0.004 seconds. Exactly same as part B. You just need to use different time. So you guys do that and tell me the answer. Force average. So what did you get?
2,700.
Okay, 2,700 newtons. Oops. And then how much force you think the player would, how much force will the football exert on the player's hand? So force on hand. Yeah, so negative 2,700, that's right. Okay. So this would be 2,700 Newton.
On this two, it's asking for the force from the ball to the player's hands on both.
How much force? Okay, so one should be, oh, the part D should be, I think there is a typo on that question. Part D is how much force the hand needs to exert on the ball, okay? And on part E is the force on the hand by the ball. So please correct the wording on part D. It's force exerted on the ball by hand. So you see that in this case there is 540 newtons force exerted on the hand by the ball, whereas in this case there is 2,700 Newton force exerted by the ball on the hand. Which one do you think the player would prefer to stop the ball? By taking a longer time or a shorter time? If you were to catch a ball, which way would you prefer? Longer time. Why is that? Yeah, so you get less force, right? So if I want to, let's say I drop this and I want to catch this, which one I prefer? So do I prefer like that or do I prefer like that? I prefer the latter one, right? Because there would be less impact force. There would be less force exerted by this object on my hand. So by increasing the time of contact, you can get less impact force. That's the theme, but that's the concept here. By changing or by increasing the time of impact, you can decrease the force of impact. So let me ask you this conceptual question. Let's say you're driving on a highway and your brakes fail. So which would you prefer? Would you prefer to hit on a concrete wall or a haystack? And why? So you want to stop your car and you have two options: hitting on a concrete wall or on a haystack. Which one do? Haystack, yeah, that's obvious, right? But why?
It won't be a sudden impact.
Yeah, so it has to do with this impulse momentum theorem. So your car is moving at certain speed, let's say 60 miles per hour, or let's say 20 meters per second. 20 meters per second. So to stop your car, you need this either concrete wall or haystack needs to exert some impulse. Okay, so let's say your car has a mass of 1,000 kilogram. 1,000 kilogram. So the purpose here is to stop your car, okay? No matter which one you use, you want to stop the car. So the final speed would be 0 in this case, or in this case. So we want to stop the car by applying some impulse. And how much impulse we need to stop the car? Impulse is given by final momentum minus initial momentum. Final momentum would be 0 because the car stops eventually. So mass is 1000 kilogram, and then speed is 20 meters per second. So impulse needed to stop the car is 20,000. Okay, let me not write the just number. Okay, I don't need to write the unit. So I need 20,000 something to stop the car. So there are two ways to impart that impulse. One is by applying larger force over smaller time, shorter time. Okay, I can use this one, or I can stop that by imparting smaller force for longer time. Okay. So for example, in this case, I can apply 20,000 newtons on the car over 1 second time. Okay, to get that. Or here I can apply, let's say, 20 Newton force over 1000 seconds, or let's say 200 Newton over 100 seconds. You get the same impulse, okay, in both ways. But this one is preferable because you exert smaller force, and in turn you get smaller force back on your car from Newton's third law. Okay, so smaller, this gives you smaller impact force, whereas this gives you bigger impact force. Okay. So by increasing the time, you can decrease the impact force. That's the idea. Likewise, if you want to jump from, like, let's say 10-story building, would you prefer to jump on a concrete floor, or would you prefer to jump on some kind of safety net? You prefer to jump on safety net, right? And the reason is to increase that impact time. If you increase the impact time, that helps you to decrease the impact force. Okay, so that's that. Let's look at number 4. Find the impulse of the net force on the ball during its collision with the wall. So a ball collides with the wall and then it bounces back. See the picture? So we want to find how much impulse the ball gets during the collision. So impulse, you can find impulse in two ways. One is by using this formula, and another one is by using this formula. Impulse is final momentum minus initial momentum. Now you need to decide which one would be applicable to this problem. Should I use this one? We don't have force or time, so we cannot use this one. That means we need to use this one. So mass of the ball, I can take this mass outside the parenthesis because it's same for both the terms. So mv final minus v initial. So what's the mass of the ball? It's 0.4 kilogram. And what's the final velocity of the ball? Final velocity is the velocity during the rebouncing of the ball, which is 20 meters per second. 20 meters per second. Now this is very important. Okay, so keep in mind, we'll be doing a lab on this one also. This one, so you keep this in your keep this in mind. So what you need to remember here is if you consider this to be positive direction, then this would be negative direction, because momentum is a vector quantity. You need to take care of the direction when you deal with the momentum. Okay, so the rebouncing is in this direction, so it's positive here. But before colliding with the wall, it's moving to the left. That means that velocity needs to be negative. Okay, so this velocity, which is the velocity during the motion along left direction, is negative. If you don't consider that sign, you will get wrong answer. So do the math. That gives you the impulse. So that's 0.40 kilogram. So 20 meters per second. Negative and negative is positive. So 0.04 kilogram. 20 plus 30 is 50. So 50 times 0.40. What's that? Is that 20? Yes, 20. Okay. So you can use either kilogram meters per second or Newton second, whichever you want. Okay. You can use kg meters per second, or it could also be 20 Newton second. That's the impulse. Okay. Now let's look at B. I think you should be able to do B after doing number 3. So impulse we have two formulas here. Which one would be useful to find force? The first one, right? So impulse is average force times time. So we want to find average force, which would be impulse over time. So let's find that. Impulse we just found 20 newtons second. Time is 0.010. So do that calculation. What do you get? Is that 500? Or no, not 500. Is that 200? 2000? Okay. 2000. 2000 newtons. That's the average force. Okay. So those are the applications of impulse momentum theorem. Now we have another law called conservation of momentum. Last time we talked about conservation of energy. So we also have conservation law for momentum, which is called conservation of momentum. So according to conservation of momentum, if there is no external force acting on a system, then its momentum is always same, okay, conserved. So if there is no external force acting on a system, the total momentum of the system is constant or conserved. And this is what we will be verifying in lab today and tomorrow. The moment of the system is conserved. Okay. So in system you can have bunch of objects. Okay, let's say you have an object, some explosive object, and it explodes into a couple of pieces, okay, with mass m1, m2, and m3. So the total mass here is m. So this is a system, and this system explodes into 3 pieces. Now, during the explosion, there is no external force acting on the object. Nothing is pushing or pulling the object, so no force acting on that. So in this case, the momentum before explosion, momentum of the system before explosion, would be equal to momentum after explosion. Okay. Another example, let's say we have 2 cars or 2 objects moving towards each other. Okay, so this is the system. This is m1 and that's m2. This is moving at velocity 1, this is velocity 2, but this is initial velocity. Initial means before collision, okay, so this is before collision. And now at some point they collide, and after collision they bounce back, they move in the opposite direction. So m2 moves in this direction at some other velocity called v2 final, and this moves in this direction at some other velocity called that m1 final. Okay, again this is the system, this whole thing is the system. So this is before collision, upper one, and the bottom one is after collision. After collision. So according to the conservation of momentum, the total momentum in this case would be equal to the total momentum in this case. Okay, so this is before collision, would be equal to total momentum after collision. Assuming that there is no other forces acting on the system. Okay, nothing is pushing or pulling the objects. So that's the conservation of momentum. If I want to write this in symbolic form, how do I write this in symbolic form? The law is pretty straightforward, but writing this in symbolic form may be a little bit tedious. Okay? So total momentum before collision. We have momentum of this first object, called that P1, and we have momentum of this second object, called that P2. And because this is before collision, so let's write subscript I for initial. Okay, initial means before collision, and that would be equal to momentum of the first one plus momentum of second one, and this is after collision, so for after write final. Okay, so that's momentum before collision, and that's momentum after collision. So we can further expand this. So the formula for momentum is m times v. So here we are talking about mass 1 and velocity of 1 and its initial. Here we are talking about mass of the second object, velocity of second object and its initial. Here we are talking about mass of first one, velocity of first one, but it's final, mass of second one, velocity of second one, and final. Okay, so that's total final momentum. That's total initial momentum. And we'll be using this in lab, so I think you will see how we use this later. So let's look at this number 5. This is the application of this conservation of momentum. So an SUV with mass of 1.8 times 10 to the 3 kilogram is traveling eastbound at 5 meters per second, while a compact car with mass 9 times 10 to 2 kilogram is traveling westbound at negative 15 meters per second. Okay, negative because it's going towards the left. Sometimes you may not be given this sign negative, but you need to consider negative sign when it's moving to the left, even if the negative sign is not given in the question. So the cars collide head on, becoming entangled. Find the speed of the entangled car after collision. So before collision, the cars are moving towards each other. Okay, that's before. And after collision, they become a single system, single mass, and they move either to the left or to the right. We don't know which way they move. Okay, so they will move at some speed v. So this one, let's say this is m1, this is m2, and velocity of this one is m1 initial. Velocity of this one is v1 initial and v2 initial, and this is, let's say, v final. Okay, what's this mass? What would be the mass of this entangled object? Yes, m1 plus m2. So this is after. So the law here is momentum before collision. This is number 5. Before collision is equal to momentum after collision. Okay, so before we have two objects. So P1 initial, momentum of this first one, and momentum of second one, P2 initial. That is equal to, after we only have one object. Okay, so P final. So what's the formula for momentum? It's mass times velocity. Mass is first mass, velocity is velocity of first one, and it's before, so I need to write I. Here, mass of the second object, velocity of the second object, and it's before, so I need to write I. Here, momentum is mass times velocity, so mass here is combined mass, m1 plus m2, and then velocity is v final. I don't need to write here subscript 1 and 2 because it's a single system, so a single combined object. So it's a common velocity for both the objects. So now the rest is just plugging in the numbers. So plug in numbers. We want to find this one, okay? So that's what we want to find. So how do I write expression for this? What should I do to write this equation in terms of just VF? Divide both sides by m1 plus m2, right? So cancel that, and VF is m1 v1i plus m2 v2i over m1 plus m2. Okay, so let's plug in the numbers and see what you get. So let's do that. So mass 1, 1.8 times 10 to 3 kilogram. Velocity 1, 5 meters per second. Second mass is 9 times 10 to 2 kilogram. And velocity is, it's westbound, so negative 15 meters per second. And then that over mass 1 is 1.8 times 10 to 3 plus mass 2 is 9 times 10 to 2 kilogram. So let's do the calculation. I don't have the answer for this one, so you guys need to tell me the answer. Does anyone have answer for this? Negative 1.67 unit is meters per second. You got the same answer? Okay. So this negative sign means the combined mass will move in the left direction. Okay. So this VF is vector 1.67 meters per second, and the negative sign means towards the west, or towards the negative x-axis. Okay, just say west. Okay. So this is the conservation of momentum, and today in the lab we'll also be talking about conservation of energy. Okay. So there are two types of collisions. One is elastic collision and the other one is inelastic collision. Elastic collision and inelastic collision. So when the two cars move towards each other, and then they collide and then they bounce back without losing any energy, then this kind of collision is called elastic collision. Okay, so there is no energy loss. The objects bounce back. Whereas in case of inelastic collision, so they collide and then they get stuck. Okay, so they become a single object. So there is energy loss. So in both elastic and inelastic collision, momentum is conserved. Okay, so momentum is conserved for both the collisions. Whereas energy is conserved only in this case. Okay, this case energy is conserved. I should say mechanical energy is conserved, but here energy is lost in some other form like heat or sound, or I should say some of the energy, some or all energy. So I would like you to give me an expression for the conservation of energy for this collision. Okay, so you have a object You have an object of mass m1. It's moving towards the right direction at some velocity v1I. You have another object m2 moving to the left at some velocity v2I. So they collide with each other elastically. They go through some elastic collision, and then they bounce back in the opposite direction. So this one moves at v1 final, and this one moves at v2 final. So this is elastic collision. That means total energy before collision, we should say mechanical energy, would be equal to total mechanical energy after collision. So I would like you to write or give me an expression like this one for this conservation law. So just like where is that? Here. I wrote this expression for conservation of momentum. I want you to write similar kind of expression for this law. It's conservation of mechanical energy. So how do you start that? Think about what objects are involved in the collision. You have this object and this object. So what are the energies in the object before collision? We can neglect the potential energy because there is no change in potential energy. Potential energy remains same. What changes here is the kinetic energy. Okay? So kinetic energy of the first object plus kinetic energy of the second object. Mechanical means you also have potential, but again potential doesn't change, so we can neglect that. And there is kinetic energy of the first plus kinetic energy of the second. Now both are same, so how do you differentiate before collision and after collision? So you use I for before and F for final or after. Now what's the formula for kinetic energy? Do you remember that? Kinetic energy is 1/2 mv squared. Okay, so 1/2 mass v squared. This is also 1/2 mv squared. This is also 1/2 mv squared. This is also 1/2 mv squared. All are same, but how do you differentiate the terms? So I'll be using 1 here for mass 1, using 2 for mass 2, 1 for mass 1, 2 for mass 2. Velocity is 1, here 2, here 1 for the first mass, 2 for the second mass, and this whole thing is before collision, so I need to use I. This whole thing is after collision, so I use F. Okay, so that's how you express them.
Do we have to put like the I after the M and after the V, or can we just put it after the
No, the mass won't change, so you don't have to put the
the 1 and the
right. So you don't have to put I for the mass because the mass doesn't change after collision, right? Whatever mass you have here, it would be same here. So there is no I here.
I meant like, can we just not put the 1 after the M and just put 1 I after the V?
Oh, you mean you don't want to put 1 here? Then then you may be confused with these two masses because these may be different. So one may be heavier than the other one. So this one is 1 and this one is 2. That's why you need these subscripts. But sometimes you may have same mass. In that case, yeah, you don't need to put the subscripts. Let's say you are colliding the objects that have same mass, then you don't have to worry about the subscripts. But if one is heavier than the other, then you need that. Okay, we will be using this also for today's lab, so that will give you a good practice. So you guys have any question? We have 3 minutes left about conservation of energy or conservation of momentum. Okay, I think that's all for this class. We will continue this next time.